Okay, so in this video we're going to do a little revision of substitution for anti-differentiation / integration. So the first thing I'm going to say is that when you would have done this last semester, it would have probably would have been called U substitution. I'm just going to change it to calling it W substitution because in integration by parts we're going to have a different U substitution, and just so we don't get confused, I'm going to use W's instead. Okay, so we would have said in the last video the last lecture that we don't have a product rule for anti-differentiation, but if anti-differentiation is what it is, and of course it is what it is, then what we can say is that we can run differentiation rules backwards, and this should give us rules of anti-differentiation. So for example, look at this function here, a composition with an outside and inside. To differentiate it, we use the chain rule. The chain rule says you differentiate the outside function, so that's v dashed, that's differentiating the outside function, but the chain rule says evaluate it at the inside. The inside here is w of x. And then it says, the chain rule says multiply by the derivative of what's inside. This means that we have a rule of anti-differentiation that if you if you differentiate v of w of x, you get this. So if you anti-differentiate this, you get v of w of x. So we get a rule of anti-differentiation that if you anti-differentiate v dashed w of x times w dashed of x, go backwards, you will get v of w of x, of course, plus a constant. This is a completely legitimate formula to write down. The problem is this is a very difficult pattern to spot. Actually, the one that I find interesting is kind of doing the quotient rule backwards. I suppose the quotient rule comes from the product rule and the chain rule. So if you can run the chain rule backwards and the product rule backwards, you can run the quotient rule backwards. Right. We're not going to run the product rule backwards until a later video. Okay, so this is basically the chain rule done backwards. And we're saying it's a difficult pattern to spot. So what we do is when you get here, you do a substitution. So if I call my antiderivative I, my job is to let w equal to w of x. Okay, now the tricky bit as far as I'm concerned is picking that w of x. We'll probably talk about that a little, well, we'll talk about it down the bottom. So you let w be w of x, and then you get a relationship between dw and dx. So what you're going to do is you're going to write this basically in terms of w. So let's see what we get. So we're going to let w be w of x. So whatever you've substituted becomes w. And then for the moment, I'm going to keep this w dashed of x here. And I want to replace dx in terms of dw. So to get a relationship between dx and dw, I need to differentiate w. So working from here, I differentiate both sides. I get dw dx is equal to w dashed of x. Multiply both sides by dx, which is nonsense. There's a comment below saying that it's nonsense, but it's okay. Now a lot of people here, once they see the w dashed of x dx, they'd replace it with dw. In my opinion, that can be a little bit difficult, so I recommend instead rewrite dx in terms of dw. So divide both sides by w dashed of x, which is more nonsense, but you can show that it's okay. So this dx is equal to dw divided by w dashed of x, and then there's loads of space here. Sorry, there's not loads of space here. So I was going to jing myself up. So w dashed of x divided by w dashed of x is 1, so that's gone. So what you're dealing with is the v dashed of w with respect to w. And this is just, well, because it's respected of. Now there's a lot of stuff in the mix here, but you got to trust that everything works okay. So it's an antiderivative. So you go from the derivative back to the original function, v of w, and of course plus c. And that's exactly what we started, or that's exactly what we, so you could say, oh, well, what you do then is you say, okay, the question asks you to antidifferentiate with respect to x. So you should do a back substitution, put in the w back as w of x. Now, what the hell is this all about? Why am I writing it like this? Because the pattern is too difficult to spot. Look, it's the same, we ended up the same thing. The pattern is just too difficult to spot, unless you have lots of practice. So strictly, okay. So how do you know if a antiderivative requires a w substitution? So that's a difficult thing. Experience is the answer, I would say. I'd probably be able to look at this stage and say if it needs an antiderivative or not. But basically what I'm recommending you do is you look in the tables. If it's not in the tables, you try a manipulation. And if the manipulation doesn't help, then you try a w substitution. That is probably what I would say to you. Okay. The next thing is how do you know how to pick the w substitution? Well, I've got some rules here. So the first one are recommendations. The first one is look at this formula here. What's the w? The w inside, what are we going to say? You see a function inside another and a multiple of its derivative. Then you let w be the function. The second one is you simply see a function w inside another one, let w be the function inside. Liate is another thing. We haven't said what liate is. We'll see that later on. Another one is just try something. Usually there'll just be two options. If one doesn't work, you try the other one. Okay. So we'll look at some examples here of this. Okay. So this question came up on the exam paper. Right. So we'll go through direct and manipulation first. So it's not in the tables. There's nothing this complicated in the tables. So what you could do if you wanted is you could write this thing, how I'll call this I, say. So I could write, I could say, okay, the square root is to the power of a half. That's something you should know, that square root is power of a half. And because it's dividing, it's a negative power. So I could write this, if I wanted, as x plus 2 times x squared plus 4x to the power of minus a half. Now, you can't multiply this in, there's nothing like that. You could split this up as x over this plus 2 over this, and unfortunately that just ends up going down the wrong track. You end up having to do what's called a back substitution, and in fact I think one of them doesn't work. The hope would just be that you don't go there. So you get to here, and really you can't multiply it out. There's nothing you can really do. The splitting up thing you could try, but actually it makes things worse. So maybe you mess around with it for a little while and you say, okay, it's not in the tables and manipulation doesn't work. I need to do a w substitution. Now we've got 3 reasons that we should try the x squared plus 4x. The first reason is, look at x squared plus 4x. Its derivative is 2x plus 4, which is a multiple of this. So that suggests you should let w be this. The other one is you could say that x squared plus 4x is inside this power of minus a half and originally inside the square root. By the way, you do not have to do this manipulation at the start, although you probably have to do it eventually. So well, anyway, this x squared plus 4x is inside another function, and by liate, so the liate is just, okay, L stands for logs, there's no logs here. I stands for inverse trig, there's no inverse trig here. A is algebraic, and liate kind of says pick the highest power. So you pick x squared plus 4x over the x plus 2. So we're going to do our substitution with w equal to x squared plus 4x. Okay, so what we said is we'd start putting this thing back together. So I, the antiderivative, is antiderivative. So x plus 2 can just sit there for the time being. Now we could work with this, but we've already done the manipulation, so we'll work with this. This is now we're saying is our w. We've got w to the power of minus a half. And now we have dx. Well, what we said is we need to go in terms of w. We end up writing everything in terms of w. So to get dx in terms of w, you need a relationship between dx and dw. That means you need to differentiate w. So you go over here and you say dw dx is equal to the derivative of x squared plus 4x. So it's a sum, so we can differentiate term by term. The derivative of x squared is 2x plus the derivative of 4x. Now, just thinking in terms of our previous chapter, let's keep up the linearity, fix the constant 4. And what is the derivative of x? At this stage, you should know that it is 1. Okay, we're trying to solve for dx, so multiply both sides by dx. You get dw is 2x plus 4 times dx. And you're looking for dx, so divide both sides by 2x plus 4. So you get dw divided by 2x plus 4. This is going to be a little bit tricky, but we'll do our best, is equal to dx. So dx, which is here, is equal to dw divided by 2x plus 4. Yeah, so this bit is a little bit tricky. So you've done the manipulation, I would say, or excuse me, the substitution. I would say that what you're looking out for is, you're looking for this cancellation as such. Now, I don't like the word cancellation, but anyway, you don't want a mix of x's and w's. It doesn't actually work. So there's surely some relationship between these two. And you kind of eyeball it for a while, and hopefully you recognize that the thing on the bottom is twice the thing on the top. So in particular, I can take out a common factor of 2. Yeah, 2x, 2 by 2 is 4. And then x plus 2 divided by x plus 2 is 1, it's gone. Now you have to be careful here, this divided by 2 is actually a half, so I can take that out as a constant, and I'm dealing with a half, w to the minus a half dx. Woo, dw. Now this is something we can work with because it's in the tables. The antiderivative of w to the minus half with respect to w. We keep the half there. We add 1 to the power, so it'll go to w to the half and divide by the new power. Good. And now we've got just 2 more things to do. The first is not as important, but on how do you multiply fractions? Top, top, bottom, bottom. So you get 1 by w to the half is just w to the half. And then 2 by a half is 1. So it's w to the half divided by 1, which is w to the half. Now this is very good, but we were asked originally to antidifferentiate with respect to x. So our answer here should be in terms of x as well. So I substitute in w is equal to x squared plus 4x. And then of course for full marks you'll need plus c. So that's a w substitution. Right, now that is something you did last semester, but any of these kind of antiderivatives can come up again in this module as well. Okay, now this one is kind of a bit scary looking. So you look at it, it's not in the tables. The only real manipulation that you could try would be writing divided by 1 plus x squared as 1 plus x squared to the minus 1. If you don't actually do that, it's not the end of the world, because this doesn't go anywhere, so you could say go back, but I think we're going to run with this. So you try a substitution. I've got 2 good reasons to pick inverse tan. The first is you've got inverse tan, its derivative is 1 over 1 plus x squared, and actually we've got a multiple of that because it's 1 over 1 plus x squared, so that's why. And liate is the other. Are there logs here? No. Are there inverse trig? Yes. Try the inverse trig. The second way, which was just try something inside something else, doesn't work very well because here you've got the 1 plus x squared is inside something else. So, you try it. So we're going to try inverse tan x. We'll just see what happens if you pick the wrong w. So the wrong w here would be 1 plus x squared. If you go through it, we'll just see where you end up. You end up here, and you don't get this cancelling as such. I hate the word cancelling, but you don't get the x's disappearing. So it's kind of failed. Sometimes in hard examples you can do a back substitution. So you can put the x back in terms of w, and you can actually do that, and you end up with this. Now look at this. You've actually made it worse, suggesting that you, in the 2 options, if you couldn't see it, function multiple derivative, you couldn't do Liate. You just said, oh, I need to pick something. You just had to chance your arm. The 1 plus x squared didn't work. There's only really two options, 1 plus x squared and the inverse tan. So we're obviously going to try the inverse tan. Okay. So let's put this thing back together. Space isn't great here, so I'll go over to the left. So I have integral e to the inverse tan. I'm taking the inverse tan to be w, so I'll write w there. And I have 1 plus x squared to the power of minus 1. That's just sitting there at the moment. And I've got a dx. I'm going to write that in I'm working from here, by the way. I've got a dx. I want to write that in terms of dw. So you need a relationship between dx and dw. You need to differentiate w. So you do dw dx. You go into the tables. The derivative of inverse tan is 1 over 1 plus x squared. And you're looking for dx here, so I'm going to multiply both sides by dx and multiply both sides by 1 plus x squared. And you get 1 plus x squared dw is equal to dx if you multiply both sides by dx, 1 plus x squared. So the dx, which is here, is in fact equal to 1 plus x squared dw. Now, if you have any hope here, you need to be reasonably good at algebra. You need to understand that the power of minus 1 means dividing. So you got 1 plus x squared divided by 1 plus x squared, which is 1. And 1 times e to the w is just e to the w. Perhaps it's worth saying that if we did not do the original manipulation, which was turning the divided by 1 plus x squared into 1 plus x squared to the minus 1, that this part would have been easier because you would have had 1 plus x squared divided by 1 plus x squared. But in general, it's not a bad idea to do the manipulation because, say, in this question, if you didn't do that manipulation, you would have had 1 over w to the half. You'd have to do it later anyway. So whether you do it at the start or the end, it doesn't matter. Here, doing it at the start wasn't so good. Okay, now we've got, this is good. This is just all w's. If there's x's and w's like this, you're going nowhere. This is good. And we know that the antiderivative of e to the w is e to the w. And then the original question, way back when, wanted to antidifferentiate with respect to x. So we should put our w in terms of x. And we remember that w is inverse tan of x. So you get e to the power of inverse tan of x. And as usual for an antiderivative, we do plus a constant. Okay. I would say this next example, we probably, we don't need, well, maybe it's probably worth doing it. There's probably just a few comments in there. It's probably worth doing it. Okay, so sine cubed by cos x is not in the tables. There are manipulations here. They're tricky. But instead what we're going to do is we're going to say that k is equal to the integral of sine of x all cubed cos x dx. Now all this is saying is that we understand what sine cubed means. It means sine of x all cubed, and that will help us a little bit for our substitution. So we just have to be wary of one thing. This notation isn't great because we use sine inverse for the inverse function, which isn't sine x to the power of minus 1. So this notation is not ideal. Okay, this is still not in the tables. We've done our manipulation. There are harder manipulations, but we won't go at them because we're just trying to show w substitution. So we're going to pick a w. Now, I've got two reasons to pick sine of x. Liate doesn't work here because no logs, no inverse trig, algebraic, no trig. There's two trigs. So it doesn't really work. But there's two reasons. W equal to sine x. Sine x has the derivative cos x, so you function multiple of derivative. W should be sine x, or else you say that, oh, sine x is inside something else, it's inside the cube. So you should let w equal to sine x. So we rewrite our antiderivative here as, okay, so this is now w cubed. We're going to let cos x sit. And now what about dx? So we want to write dx in terms of dw. So to get a relationship between dx and dw, you need to differentiate w. We need to differentiate w is equal to sine of x. Differentiate both sides. You get dw dx is equal to cos of x. And then you're solving this for dx, so multiply both sides by dx. And I recommend dividing both sides here. You're looking for dx, divide both sides by cos of x. So dx, in fact, is equal to dw divided by cos x. Okay, so now the nice thing happens, cos x divided by cos x is 1. And you've got simply the antiderivative of w cubed with respect to w, which is no problem, it's in the tables. It's w to the 4 divided by 4. And then, well, we were asked originally to antidifferentiate with respect to x, so we should put w back in terms of x. W is sine of x. So you get sine of x all to the power of 4, which you could write, by the way, as sine to the 4x, but we won't worry about it, over 4 plus c. The one final remark here that I should have mentioned is that when you're doing a substitution, if you have time, you can actually check. If you're good at differentiating, you can check your answer by differentiating. So you differentiate this, do you get sine cubed cos x? Differentiate this, do you get what you started with? If you differentiate this thing, do you get this? I would say that because the W substitution is running the chain rule backwards, all of these things need the chain rule to differentiate them, because they're all outside, inside, outside, inside. Okay, so that's W substitution, officially still review.